You settle into the seat of your time pod. On the flickering dashboard, you punch in 480 BC. Your goal is to see the legendary Battle of Thermopylae with your own eyes. You hit the launch button. There is a blinding flash of light, and in the next fraction of a second, your blood instantly boils, your lungs rupture from decompression, and your retinas crust with ice. You smell no dust or bronze. You see no Spartans. You are suffocating in the empty, pitch-black vacuum of deep space, billions of miles from the nearest heat source. Welcome to the actual physics of time travel. For decades, pop culture has spoon-fed us the same visual template. The hero winds back the calendar, and the world changes around him like a theatrical backdrop, all while he remains standing in the same parking lot. A tired plot device? No. It is an arrogant insult to the laws of astrophysics and the basic laws of motion. Common sense tells us that if you turn back the clock, your house will still be standing in the same place, but as Einstein astutely noted, our so-called common sense is merely the collection of prejudices acquired by the human brain by age 18. Our biology, which evolved on the surface of a single planet, has hardwired us to perceive space as a stationary stage. But the universe despises stasis. Space as a fixed coordinate grid simply does not exist. The Earth does not hang in the void on an invisible nail. To reach ancient Greece, you can't just rewind 2,500 years. You have to find the planet first. At this very second, our globe is hurling along its orbit at 30 kilometers per second. The Sun itself, carrying monstrous inertia, is plowing its way through interstellar gas, revolving around the center of the Milky Way at 220 kilometers per second. Our entire galaxy, along with neighboring Andromeda, is falling toward a colossal gravitational anomaly, the Great Attractor, at 550 kilometers per second. Travel back in time and you will arrive at the exact same absolute spatial coordinates. The Earth vacated that spot millennia ago. Consider the European Space Agency's Gaia Space Telescope. Orbiting at a Lagrange point, the probe has spent years tracking the minuscule displacements of billions of celestial bodies, their parallax. The data from recent catalog releases have provided us with precise 3D cartography of the galaxy. Visualize this dataset, and instead of a frozen textbook map, you'll see a frantic swarm of glowing particles rushing in different directions along incredibly complex trajectories. Returning to the past to the same coordinates is mathematically akin to firing a sniper rifle and hitting a bullet in flight that was fired a century ago from another continent. Sci-fi writers sometimes try to lend a veneer of hard science to their plots by discussing the problem of overlapping matter. They write about how air molecules might end up inside the time traveler's blood vessels, causing an embolism. Compared to real macroscopic astrophysics, the problem of synchronizing with constantly fleeing star systems is orders of magnitude more daunting than a random nitrogen bubble in a vein. Any time machine must, first and foremost, be an engine of absolute spatial displacement, capable of bridging millions of light years of void. But to build such a navigational complex and rigidly tether its route to the axis of time, we must discard familiar Newtonian mechanics. We must turn to equations whose very creator refused to believe what an uncontrollable gravitational monster he had unleashed on paper. Let's dissect this monster piece by piece. Travel to the future has already been invented, not as an abstract hypothesis, as a proven engineering fact. According to the 1905 special theory of relativity, you simply need to place an astronaut in the centrifuge of an interstellar ship and fire the engines until you reach 99.9% the speed of light. For the pilot, pinned to their contour seat by crushing g-forces, mere months will pass. The biological aging of their cells will slow down in sync with the rhythm of the onboard quartz clocks. But when they finally touch down on Earth's landing strip, they will discover that dozens of generations have come and gone. You will step out of the airlock into a world where everyone you ever knew has been dead for ages. Indisputable and mathematically sterile, no time paradoxes. Think about what that actually means. Future travel is not a hypothesis. It is solved. The only question is whether anyone will ever build the ship. The trouble begins when we try to reverse this chronological vector. The equations of general relativity predict that gravity is not an invisible thread pulling an apple to the ground, but a physical warping of space-time itself. If an object's mass is large enough, it can tear through this three-dimensional grid, collapsing into a point of zero volume and infinite density, a singularity. The human mind rebels against infinities. Even Einstein, who penned these equations himself, was horrified by his own calculations. In 1939, he published a paper in the Annals of Mathematics, flatly denying that such objects could ever form in nature, calling them mathematical ghosts, not physical reality. But therein lies the ultimate, slightly cynical beauty of physics. Real science begins where your own mathematical model couldn't care less about what you personally believe. The laws of the universe do not seek the approval of their discoverers. Einstein was genuinely mistaken. His formulas were not. Point a radio telescope's mirror into deep space, and you will see the reality of gravitational collapse with your own eyes. In the late 1950s, astronomers locked their sights on quasars, supermassive black holes at the centers of distant galaxies. Their gravity grinds, compresses, and heats infalling gas until the accretion disk blazes with blinding light that pierces through billions of light-years of void. Quasars seemed to be the definitive answer to the nature of gravitational collapse. But that was a mistake, not in physics, but in hubris. The James Webb Space Telescope posed a far more uncomfortable question to our models. Its infrared sensors detected objects that shouldn't exist according to the current rules. Quasars and galaxies assembled within the first billion years after the Big Bang. Larger, heavier, and earlier than any accretion model can explain. Patches were proposed, some of the tension eased, but with each new JWST data release, the list of objects in the wrong place at the wrong time keeps growing, and the patches keep multiplying. At some point, a model that requires this many patches stops being a model. It becomes a negotiation. Space-time is capable of twisting into knots far more radically and rapidly than we ever dared to imagine. Physicist John Archibald Wheeler, the man who gifted the world with the term black hole, knew perfectly well that the warped geometry of the cosmos hides other structures. He later introduced a different, much more intriguing concept into the scientific lexicon: the wormhole, a shortcut through the geometry of space-time. A black hole is a gravitational crypt with no exit, the absolute end of any route. A wormhole mathematically promises a transit tunnel, directly connecting two distant points in the galaxy, bypassing the cosmic speed limit. But if we physically detach one end of this spatial bridge and apply the relativistic time dilation from our first spaceship experiment, a door swings open, revealing logical anomalies permitted by physics. Let's construct a hypothetical but geometrically consistent structure. A traversable wormhole, a spatial tunnel with two open mouths. We rigidly anchor one mouth in Earth orbit, and we load the second into the cargo bay of an interstellar cruiser. We fire the plasma engines at full throttle, accelerate the ship to near light speed, send it on a long voyage across the galaxy, and bring it back. According to special relativity, external time for the flying object will drastically slow down. Millennia will pass on the planet, while the astronaut ages only a single year. Inside the tunnel itself, however, time continues to flow synchronously for both ends. The result of this manipulation is simple. The two mouths have desynchronized in external time. Enter the Earth-side portal in the year 5000, and you will exit the ship-side mouth in the year 3001. Calculations by leading theoretical physicists confirmed this. We have just assembled a portal time machine out of pure gravity and relativistic geometry. The traditional fear regarding this scenario is the classic grandfather paradox. If you return through this tunnel and eliminate your ancestor, you will never be born, meaning you could never go back. Either the logic of causality crumbles, or travel to the past is fundamentally impossible. Physics has an answer for this. It is not a comfortable one. Theoretical physics later formalized the self-consistency principle. The laws of nature are engineered so that the probability of any action leading to a paradox is strictly zero. Space-time is deterministic. The gun will misfire. You will miss because of a sudden muscle spasm. Grandpa survives, the past is immutable, and your desperate trip back in time is already written into history that ultimately led to your birth. Free will does not exist within a closed relativistic loop. You are merely a marionette dancing on the strings of warped space-time. Which answer is more unsettling, that the past cannot be changed, or that your choice to try never existed in the first place? Finding a natural wormhole in deep space while simultaneously hitting a coordinate that a planet vacated billions of miles ago isn't just difficult, it's operationally impossible. However, later cosmological models proposed an elegant alternative metric that permanently spares the navigator from having to hunt for natural anomalies. A spacecraft traveling at sub-light speed flies toward a distant star, artificially generating and leaving behind a specific space-time channel in the vacuum, a kind of wake of deformed space. On the return trip, gliding through this isolated tube, the ship travels faster than light relative to an outside observer. The ship didn't outrun the clock, it made the clock irrelevant. The mathematics of a Krasnikov tube bend until something remarkable happens. The astronaut returns to Earth at the exact same moment they left. You aren't looking for a pre-existing door to the past. You are laying your own temporal tracks, stitching the start and finish lines into a single chronological point. Try mentally removing the supporting force fields from any of these structures, be it the throat of a Thorn wormhole or a Krasnikov tube. Dictated by the laws of general relativity, the tunnel walls will collapse under their own supermassive weight faster than a single massless photon can slip through. To hold the tunnel open, its architecture must be flooded with a medium possessing negative pressure, a substance with a gravitational repulsion effect. This concept, later dubbed exotic matter, was rigorously derived decades ago by dissecting the physics of vacuum-like states. Negative pressure is not sci-fi fantasy. It can be demonstrated via the very real quantum Casimir effect. Place two uncharged mirrored plates a few nanometers apart in a deep vacuum, and they will inexplicably begin to attract each other. Virtual particles popping into existence on the outside push harder than those spawning in the narrow gap between them, creating a zone of negative energy. We simply need to scale up this microscopic quantum magic trick to the size of an interstellar ship. Without this anti-gravity scaffolding, any spatial architecture becomes a death trap, crushing the traveler into singular dust. I went back and read the peer-reviewed objections to these models. The consensus confirms the same thing. Exotic matter is required, and nobody knows how to produce it at the scale we need. That's where the papers end, not with a proposed solution, just a shrug. The conversation stops exactly at the moment it should have gotten interesting. We are forced to descend to the level of quantum fields in search of this exotic glue capable of prying apart the walls of time. It is there, plunged into the microcosm, that we discover the universe is no passive spectator to our engineering ambitions. It has a failsafe written into its own geometry, one that incinerates anyone attempting to hack its chronology. On paper, a macroscopic wormhole held open by exotic matter looks like a triumph of geometry over linear time. But the moment those two mouths align, the moment even a single photon could slip into the past, the microcosm wakes up. Virtual particles, electron-positron pairs erupting, colliding, vanishing in the vacuum around us, are captured by the tunnel's gravity. A photon travels through the wormhole, goes back into the past, exits, and immediately flies right back into the same mouth at the exact moment it did so the first time. This cycle repeats an infinite number of times in a fraction of a second. The process creates a catastrophic feedback loop. The physics of this phenomenon are identical to the deafening screech of a microphone held right up to a speaker, only here what's circulating is pure energy. Calculations proved that this avalanche-like buildup of quantum fluctuations will burn the wormhole to ash. Any gravitational chrono engine will detonate in a blinding flash of gamma radiation exactly 1 instant before it is actually activated. Stephen Hawking elevated this radiation glitch to the status of an immutable law. His chronology protection conjecture states unequivocally, nature actively prevents the formation of closed time-like curves. The conjecture is unproven by definition, but somewhere between Hawking's blackboard and the textbooks, that distinction quietly evaporated. The universe preemptively destroys the very geometry of any time machine before it can damage causality. This isn't a technical oversight by engineers. It is a radiation shield hardwired into the very fabric of our physical laws. General relativity obediently permits gravitational time loops. Quantum mechanics incinerates them. This creates an insurmountable paradox. The two foundational theories of the 20th century, which underpin all of modern physics, outright contradict each other when trying to describe the same event. A mathematical proof of their incompatibility was obtained long before the era of black holes. The first attempts to quantize gravity hit a conceptual dead end. Visualize this conflict, and you will see two worlds colliding. On one side is the smooth, continuously flexing relativistic fabric of spacetime, like a taut trampoline. On the other is the quantum foam at Planck scale, discrete, probabilistic, seething. When we try to merge Einstein's smooth curves with microscopic chaos, the formulas spit out infinities and lose all physical meaning. Gravity breaks down at quantum scales. Have you ever tried to examine a digital photograph under a high-powered microscope? From a distance, you see smooth, continuous gradients of light and shadow. That's Einstein's metric, the smooth canvas of gravity. But zoom in close enough, and the seamless picture abruptly fractures into a crude, discrete grid of square pixels. In reality, these pixels would be the Planck quanta of spacetime itself. To resolve this theoretical clash, science needs a new mathematical architecture, a theory of quantum gravity. Only this yet unwritten theory can answer whether directed travel to the past is possible for macro objects. And only when we understand exactly what minimal building blocks the cosmos is made of will we know whether its own laws permit rewriting, or whether any attempt to do so ends the same way every time. Let's cool 9 superconducting qubits of Google's Sycamore quantum processor down to near absolute zero and force them into a state of deep quantum entanglement. In a series of experiments published in the Nature journal between late 2022 and 2024, a team of physicists performed an unprecedented engineering miracle. They injected quantum information into one part of the qubit system, scrambling the signal into unreadable chaotic noise. A moment later, that exact signal reassembled perfectly and emerged from the other side of the processor. No physical tunnel was built in the lab. Yet the mathematical dynamics of exactly how the information traversed the entangled qubits turned out to be bit for bit identical to what you'd expect from a gravitational wormhole at macroscopic scale. The simulation proved a radical hypothesis that quantum entanglement and wormholes are not two different phenomena described by the same math. They are the same phenomenon described in two different languages. Space itself is not a monolith. It is woven from quantum information, like a holographic illusion generated by particle interactions. If reality allows us to program holographic gravity tunnels into microchips, a subsequent, far deeper question arises. Are we capable of isolating an artificial quantum ensemble and forcing its local time to flow backward right before our eyes, violating the supreme law of thermodynamics? In the macroscopic world, a shattered porcelain cup will never rise from the floor back into your hand, reassembling its shards into perfect form. A system's entropy increases without exception, driving everything in one direction. The thermodynamic arrow of time. Stars cool, cells age, the universe marches toward heat death. But zoom into the microscopic scale and something breaks. The equations of quantum mechanics don't care which way time points. They run equally well in both directions. Between 2019 and 2024, an international team of quantum physicists committed an act of direct computational violence against the second law of thermodynamics. Taking a quantum computer, they targeted an isolated system of qubits with precisely calibrated microwave pulses. In their natural state, the particles' quantum states scattered chaotically, bowing to entropy like billiard balls after a break. An external phase reversal algorithm, a microwave kick, was then applied to this scattered chaos, forcing the wave function to evolve backward. The qubits instantly reassembled into their original pristine state. The researchers didn't just simulate a software rewind. They physically forced a real quantum system to return to its own past for a fraction of a second, violating local thermodynamics. Time can be reversed on one condition. You must have absolute external control over the quantum ensemble. Let's place a boundary between two physical mediums inside a vacuum chamber. Standard metal and a chunk of superconductor cooled by liquid helium to near absolute zero, where electrical resistance drops to zero. We fire a single electron from the metal straight into this invisible temperature wall. Kinematics strictly dictate that the particle must either punch through the barrier, losing energy, or bounce off elastically. The universe, indifferent to our list of options, selected neither. Decades ago, quantum physics described a mechanism that sounds absurd, yet has become an undeniable experimental fact of modern electronics. The electron slams into the superconducting barrier at immense speed. It drastically lacks the energy to exist there alone. Instantly, it snatches a neighboring electron from the metal, forms a Cooper pair, and slips effortlessly into the superconductor. The laws of conservation of charge and momentum demand immediate compensation at the point of impact. As a result, an antiparticle with a positive charge, a hole behaving like a perfect positron, bounces off the boundary and shoots back into the metal. It flies exactly along the original electron's trajectory at the same speed, but in reverse. The reflected antiparticle is not a new object generated from the void. It is the very same electron, its chronological vector literally turned inside out from the impact with the superconductor. The particle has begun to physically move backward in time. To be precise, this is the Feynman-Wheeler interpretation, not the standard language of condensed matter physics, which prefers the more neutral term whole and stops short of invoking temporal reversal. But the mathematics of both descriptions are identical, and mathematics doesn't negotiate based on what we find more palatable. Imagine the mechanics of this process on a human scale. You walk up to a concrete wall, slam into it hard, but instead of bouncing off with a bloody nose, you dissolve into the concrete. And in that same second, your mirror double, woven from antimatter, steps out of the wall and walks backward in your footsteps toward yesterday morning. Antimatter is the mathematically inevitable echo of the future, crashing against the present and rolling back into the past. But if antimatter is simply regular matter being forcibly driven from the future into the past, the scale of this chronological symmetry spawns a paradoxical conclusion about exactly whose endless copies our boundless cosmos is actually constructed from. My deep subjective admiration for the American physicist Richard Feynman rests less on his Nobel laureate status and more on his cold intellectual fearlessness. Where other academics saw mathematical dead ends and diligently averted their gaze, he coolly dissected the hidden gears of reality, laying bare their mechanics. The pragmatic shut up and calculate paradigm, see the formula, see the abyss, step back, is not methodological rigor. It is a way to avoid making eye contact with what you yourself just discovered. I find that habit more limiting than any equation. Feynman didn't know how to retreat, or simply refused to. He viewed physics not as an abstract set of symbols on a chalkboard, but as a deterministic mechanism of interacting information fields. In the spring of 1940, Feynman was still a graduate student at Princeton. His advisor, John Archibald Wheeler, called him. Wheeler said, "I know why all electrons in the universe have the exact same charge and the exact same mass, because they are all the exact same electron." Wheeler never proved it. The idea remains officially classified somewhere between brilliant and untestable. Physics departments tend to admire it and then quietly move on. But follow its logic to the end, and the implications stop being comfortable. The observable universe is packed with trillions upon trillions of electrons, and all of them are laughably identical, as if stamped out on a single cosmic assembly line. Standard quantum field theory explains this as local excitations of a single universal field. Wheeler rejected this compromise, proposing a mathematical framework that blurs the line between physical multiplicity and an endless loop of time. Trace the path of a single fundamental particle ejected into space at the moment of the Big Bang. This lone electron flies through the empty cosmos billions of years into the future, right up until the heat death of the universe. There, colliding with the thermodynamic end of time, it physically turns around and flies back into the past. Now, our instruments register it as a positron, an antimatter particle with the opposite charge. Reaching the 0 point at the dawn of time, it bounces off the initial singularity once again and flies forward. This world line doesn't stop. It zigzags back and forth, stitching through the entire history of the cosmos, like a single thread in a four-dimensional loom. When we look at our own hands, at silicon microprocessors, or the plasma of distant stars, we are merely seeing billions of temporal slices of the same particle, piercing the current moment in different directions. Antimatter is not an exotic substance, but the inevitable kinematic consequence of a particle moving in reverse along the axis of time. If all matter consists of a single fundamental unit, the illusion of our multiplicity is sustained only by the human brain's biological inability to perceive time as a single monolithic block. But if the very foundation of our flesh and blood can so easily ricochet from the future to the past, why can't we scale this quantum loop up to human proportions and build a full-sized time machine? The answer is hidden within the greatest unresolved conflict in modern science. A lone electron juggles the direction of time, bouncing off the thermodynamic walls of the universe. A human being is built from octillions of those same electrons, locked together, chemically bonded into a structure of staggering complexity. Try to force that entire architecture backward against time, you immediately hit quantum decoherence. Interaction with the environment will shatter the fragile symmetry in microseconds, turning ordered information into chaotic white noise. The macroscopic biological system will disintegrate into subatomic elements in a flash of radiation long before its chronological vector even approaches the zero mark. What is permitted for a single fundamental particle is categorically forbidden for a highly complex composite object. The mathematics of the macro world and the micro world are governed by conflicting, incompatible equations. General relativity bends space into elegant gravitational loops, ensuring us that physical portals to the past do exist. Quantum mechanics switches on radiation censorship, incinerating any engineering attempt to close a macroscopic loop. None of our existing, thoroughly verified physical models provide a coherent picture of the universe. Science is at a stalemate. Both great theories work flawlessly at their respective scales. Einstein perfectly describes the orbits of galaxies. Quantum physics perfectly describes lasers and microprocessors. But when we try to stitch them together at the edge of a singularity or inside the throat of a wormhole, the formulas go mad, spitting out absurd infinities. Controlling chronology is not a task of screenwriters. The barrier between us and time isn't technical. It is hardwired into the very nervous system we use in our attempts to overcome it. Our nervous system constantly convinces us that we are passive observers, passengers trapped in a biological spacesuit, obediently hurtling along the tracks from the past into the oncoming future. If the theory of quantum gravity one day proves that time is an emergent illusion, woven from entangled information at Planck scale, then the person in that pod, fingers above the dashboard, isn't preparing to move through time. They're already inside it, indistinct from every other event in its structure. The dashboard is still flickering. The coordinates still read 480 BC. The launch button is right there. The physics has not changed and will not change, and has never been waiting for you to be ready. The universe makes no allowances for expectations, and there is a bitter consistency in that. It never created them in the first place.